A record-breaking gravitational wave puts Einstein's gravity to the test. Scientists have detected the clearest gravitational wave ever recorded from two colliding black holes, and it has provided one of the strongest tests yet of Albert Einstein's theory of gravity. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. The signal, called GW250114, matched Einstein's predictions with remarkable precision. That confirmation is impressive, but just as important, it gives researchers hope that future signals might eventually reveal where Einstein's theory breaks down and point the way to new physics. What are gravitational waves and why do they matter? Gravitational waves are tiny ripples in space and time created when massive objects move violently, such as when two black holes crash into each other. These ripples travel across the universe and can be detected on Earth using extremely sensitive instruments. GW250114 was produced by two black holes merging far away in space. The resulting ripples reached Earth on January 14, 2025, where they were detected by the LIGO observatories in the United States, along with partner detectors in Italy, Virgo, and Japan, KAGRA. What makes this event special is not just the collision itself, but how clear the signal was. Why this signal was so special? Scientists first detected gravitational waves in 2015. That historic signal, called GW150914, proved Einstein right and opened a new way to observe the universe. GW250114 is similar but far clearer. The event itself looks very much like the first one we ever saw, explained physicist Keith Mittman of Cornell University. The difference is that our detectors are much better now, so we can see the details far more clearly. In simple terms, scientists didn't just hear a faint thump, they heard distinct notes from the collision. Black holes ring like bells. When two black holes merge, the newly formed black hole does not immediately settle down. Instead, it vibrates briefly, much like a bell after it's struck. Each vibration produces a specific tone, defined by how fast it oscillates, how quickly it fades away. According to Einstein's theory, these tones depend only on the black hole's mass and spin. That makes them a powerful test of gravity. If scientists measure multiple tones and all of them point to the same mass and spin, Einstein's theory passes the test. That's exactly what happened with GW250114. Einstein passes for now. Because the signal was so clean, researchers were able to measure two distinct tones and place limits on a third. All of them lined up perfectly with the predictions of general relativity. If those tones didn't agree, Mittman said, we'd be forced to rethink our understanding of gravity. But this time, Einstein's theory held strong. Why scientists hope for a future surprise? Even though general relativity passed this test, physicists are confident it is not the final theory of gravity. Einstein's equations cannot explain dark matter, dark energy, or how gravity fits with quantum mechanics, the theory governing the smallest particles in nature. Because of these gaps, scientists believe that at extreme conditions, like black hole mergers, small deviations from Einstein's predictions may eventually appear. If we see even tiny differences in future gravitational waves, Mittman explained, that could be a sign of a deeper, more complete theory of gravity. Listening for new physics. GW250114 shows how powerful gravitational wave astronomy has become. With better detectors and more observations, scientists are now able to test gravity in ways that were impossible just a decade ago. This signal confirmed Einstein once again, but it also sharpened the tools scientists will use to challenge him in the future. One day, a gravitational wave may arrive that doesn't quite fit the rules, and when that happens, it could lead to a breakthrough in our understanding of how the universe truly